You know, guys, as I try to dive deep into how disk drive works, how disk controller drivers work, how the operating systems work, and how the database work, the whole thing is so confusing, is really putting it lightly. But that just tells me that we really don't talk to each other as engineers. You know, the disk drivers does its own thing, the operating system developer does its own thing, the database developer does a thing, and of course the backend engineer does. Definitely we do our own thing, and we never talk to each other, and as a result, so much things that we assume are true are not really true. And I'll give you an example. Like the title of this video is like how the disk lies, right? The lies of the disk drives. If you actually write something to disk, forget about disk. If you actually in the app says, hey, open file and write blah to this file, you would think, and save that file, actually Control S on that file, right? Or whatever the operation on in the API. You would think that is actually saved, right? On disk. There are literally many layers of caching going on. The first layer of defense is if you're using a database, that's the buffer, the shared buffer cache, which is a shared memory allocated by the database, usually using a map. And then that's multiple processes of that databases will write to this beautiful shared place, and it's just single place for all the pages and index pages goes there. So that's one layer of defense. It's a cache. Then when the database says, hey, write, the operating system has its own layer called the file system cache, because most databases are built on operating systems, and most operating systems use file systems to write to, block devices, right? So you need a file system. I say need. I don't agree with that. I see that a lot of people just use file system, but I'm yet to see a database that doesn't use a file system. And I know I'm talking out of my ass because I don't know anything about this, but just objectively looking at this stuff, the database does not need a file system. It just happened that we databases are built on top of general purpose operating systems. And as a result, general purpose operating system give you a file system to write files with, and databases use that. I don't see any reason why the database just talk directly to the disk drive. You build an operating system as a database. That's a fantastic idea. Cut the middleman, right? And do exactly what the database needs. Anyway, this is another topic for another day. I want to just explore it and just think about it, right? People might have thought about it, but I'm just thinking out loud here. You see that when I do the write, these writes go to the file system page cache. It refers to the file system page cache, which is mapping the virtual memory pages effectively, right? Because we're using almost always the virtual memory when operating systems. And as a result, when we do that, the file system caches this. Okay, this file, right, that you wrote these blocks, and it's mapping to these pages, and it writes it there, and it keeps it in its own memory cache, another place for the file system page cache. And then later, the hope is these pages in memory will receive more writes from the application, such that the operating system will finally buffer all these writes and then write it once to the disk, right? So that's the hope. It's called buffer.io. Why? Because if the app just directly write, every write will go directly to the database. Oh, not the database, to the disk. While this is good for persistent durability, it's chatty and it will reduce the lifespan of the disk eventually. Because while we claim we're good as engineers, we rarely, know what we're doing. We will do mistakes such as do a loop and write to the same file 100 million times in a second. And if we do that and the OS is not there to protect us, that disk will be thrashed with writes for the same LBAs, effectively, moving things around, doing all sorts of, garbage collection and, moving things to the order of provisioning and, erasing blocks and moving valid pages. It just does a lot of work to keep to satisfy your stuff. And so that's why we have an operating system page. But then eventually the OS will say, okay, I'm thinking good, and this is up to the OS. The OS will say, okay, let's actually sync. They say it's called Fsync. Why F? Maybe it's called force. This Fsync operation, right, will synchronize what I have in the file, page, data, and guess what? The file system is not free. It comes with its own overhead. It comes with its own metadata, right? All the inodes and the B trees, to maintain the directories and, all that stuff, the information, the permissions, the owner of the file, all this stuff, all the metadata, right? So if you do an Fsync, or the OS decides to do an Fsync, it will just slam everything, says, hey, disk, right now, I want you to flush all this stuff right now to disk. Just, it will just write everything, right? It will synchronize anything that is in its memory to the disk drives. Here's the final level of defense. When the disk driver, the driver is in the kernel, right? The operating system, right? That will receive that operation, and it will transmit that request, and it will, with all the data, to the drive. So the SSD or the hard drive will receive the stuff, and it actually gets a choice, because the first thing that these writes goes to the another cache, the disk cache themselves. Right? It's a small, tiny, I think around 100 megs maybe in certain devices, and those data goes there, including the file system, because at the disk we don't really know what is a file, what is not a file. It's just blocks, all LBAs, which translates to PBA, physical block addresses, which is the blocks, which translates to pages, and I'm not going to go there. The page, the word page is so overloaded when it comes to these stuff. So now when you do these writes, the disk driver will say, you know what? You've been writing to me a lot. I'd rather keep this stuff in my cache. And that's the lie here. That's the lie. While we say we write, the disk will keep this data in its own cache until later it will flush it to the media. Hey, disk, go and actually flush whatever you have. Whatever you have, go and flush it right now. Now the SSD is sitting there with, tons of megabytes of cache. I'm going to take everything I have and I'm flushing to disk. Here's where the I/O will suffer, because that operation is going to be expensive, because I can have 100, 200 megabytes of cache, and now I'm actually writing it to the media. Right? So here's the second lie that the SSDs and disks do. Some SSDs will ignore the flush and will just know up. It says, hey, I know you're flushing, but you've been flushing a lot. You don't know what you're doing, OS, or whoever is calling the OS. You don't know what you're doing. I'm just going to ignore you. Hussein from editing coming in here. After I edited the video, I found an article, a bug from Mozilla Firefox version 3, posted 15 years ago, 28 on that time frame, where we're going to read the bug right now. And boy, it's interesting. Let's read it. Let's read the bug. And then we're going to come back to the video. It's ridiculous. I love this stuff. This comes from Nathan G. Grin. He's a reporter. He's the one who reported this bug. I have been using Firefox 3 nightlies for a while. Firefox 3, I was like, what is the current? Wait a minute. Firefox is now 112, right? This is Firefox version 3, right? So you know how old this issue is. I've been using Firefox 3 nightly. It's not even the stable version. He's using a nightly. I have been recently experiencing really bad system responsiveness and have been pulling my hair out to figure out why. I know Firefox 3 seemed to be worse affected. I then found out and then I found mention of the issue I was seeing was related to Fsync, which is the same function that we talked about that actually causes a flush to disk, right? And it blocks until everything is written to disk. I used strace, which is a Linux function that can trace what the application is doing, to check Firefox 3 and found it's using Fsync like 8 times for every new page. Every new page it writes, it calls Fsync like 8 times on it. And that really exacerbated the problem, because again, this is 15 years ago when disk drives, I don't know, SSDs were there. I think SSDs was just coming to life, right? At that age, at that era. But man, Fsync 8 times per page, that just kills the performance, because now you're telling this cache, it's like flash, 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 flash. Not only the cache, you're telling everything on the page, the OS cache, to flush to disk, and then actually forcing the disk driver cache to flush everything it has, not from you, from every other host, from every other application that has cache, just a bunch of log, to flush to disk. And that is the result. So this case was received all sorts of attention, and I think it's main reason why disk drivers now ignore flush most of the time, because they say, hey, the application developer definitely doesn't know what's behind it, so the cost becomes very, very expensive, and as a result we had to do this. Back to the video. So you don't know what you're doing, my friend. You don't know what you're doing, so I'm gonna ignore it. But Hussein, isn't that dangerous? It is dangerous, because if I tell you to flush, let's say these are actually wall, journal, redo logs, right? Which is very critical. If the database tell you to write, you better write them to, you better be durable, right? When I tell you to write, these wall records are the most important thing. If you lose the wall, you're done, right? When it comes to the databases, you're just corrupted, right? So if the drive is actually ignoring the flush, I'm going to come to why, then we lose power. Whatever's in the disk cache will be lost, right? And whatever in the OS cache, of course, will be lost. And whatever in the database cache will be lost. So this persistent, is that the final thing? When I tell you to flush, the disk is ignoring flush, and we lose power. We're going to lose the data. Here's some, the reason some SSDs ignore this is because they know they do that because they have a capability that even if power is lost, they have battery included with it, temporary battery, such that even if I lost the power, I still can live. I will detect the loss, but I'll be still running on the battery. And while I was running, I was like, oh shit, I need to write this stuff. Poof, it's gonna write immediately after the detection that the power loss, right? And we're good, right? So we can ignore the flush commands, because most of the time that comes because the disk doesn't trust the OS or the host, right? We say the host mostly, not OS, because you can have disks that run directly on an application. I mean, you can literally, never done this, but you can write your own app, such as it uses the NVMe driver directly without the OS, right? Without any file system, you can just build a block and then write it to the NVMe. I don't see why not. Pretty sure all these cloud providers do that at the low level, and that's just another ball game, right? So yeah, disk slice. And that's where all the configuration, where Postgres comes in. Just an example, because I'm trying to learn more about this database. Like Postgres gives you all these fine-tuning abilities, right? There is an option when you open a file for wall writing, WAL, says, hey, I want to open with Fsync, which is open_sync. And that means every write that I do, just don't think. Don't put it in your cache. Yeah, you can put it in the cache, but the moment I say write, block me, please. I want you to block me and tell me when you actually if you wrote everything into the disk, and then come back. And when you return, you say, hey, all good. Postgres has another option where we'll give you, no, I want to open the file, which is the walls, with an option called desync or desync, which is the difference between Fsync and desync means Fsync means if I want you to write and flush everything right there and write. And when I write everything that you have in your files in the page, that includes my data and the metadata for the file, the permissions and owners and all that other stuff, the group permission of the file system metadata, which can be large, right? So there is another option that say, hey, desync, I want to open this file such that every write only write the data. You can lazily write the metadata later. So that's another thing. There's another option to open direct, which is the most confusing option in existence, right? I can make a whole video, a podcast just talking about direct. Direct is a way for the app, in this case the database, to directly bypass all the cache and write directly to the disk, right? And this is done through something called the DMA, the direct memory access. There is a coordination happening with the operating system here, such that the database will ask the OS, says, hey, give me a little bit of nice contiguous memory, and then asks the disk if I want to write, for example, the OS, the database will write to this location, and then the memory, the disk controller will immediately read directly from this. So you're writing directly to the disk. There is no page cache at all, right? And vice versa. When you read directly from the disk directly to the user space. There is no kernel space when it comes to direct. It's just a direct thing. Direct memory is so fast, and there is absolutely no page cache. You're bypassing all that stuff, and that's the power of direct. What's the problem with that? The database better know, or the app in this case, better know what it's doing, because now the OS is not there to protect you. You wrote something, you corrupted, it's your fault. Right? All of this stuff. Now, what happens with file metadata and all that other stuff? Again, it's very complex, all that stuff. So yeah, that's another option, direct. Some Postgres also gives you another option, such that if you enable this Fsync, you can say, you know what, I want you to delay all this wall writing. It's expensive for imagine every wall I write, every transaction I execute, every update I do, it just writes to the disk directly. No. It's okay. I'm a transactional system. What I want you to guarantee is if I say commit, then everything gets committed, actually written. That's all what I'm asking for. And here's where you can also play games, right? So you can open the file normally for write, but at the commit, when you actually physically do a transactional commit, the backend, which is the database, will issue a command says, okay, I'm gonna call fsync only at the commit. Physically call fsync only at the commit, not for every single write, right? And that is so powerful because now all the transaction, if that's a long transaction, these can be written to memory. When I say memory, God, what is memory anymore? All right, is it the buffer, shared buffer, or is it the page cache? Or that's what we mean basically to the page cache, right? At the kernel page cache, and that's fine. Then later we'll flush it when we do a commit. You better block me when I say commit. Block me until everything is written. And that there is another option, which is called fdatasync, right? Which tells you on commit, when you commit transaction, it will only flush the data, which is the wall entries, not the metadata of the files that belong to the wall. Does that make sense? There's one final option in Postgres that I forgot to mention is you can turn fsync off altogether for wall writing. What does that mean? It means that you don't care if you commit a transaction or you write anything to the wall. It is fine for you to write the information to the page cache in the file system and return immediately. It is okay not to run fsync and actually write all these pages to the disk controller, which will eventually get flushed from the cache down to the media, the NAND cells. That is fine. The danger, of course, you are getting into a situation where if the crash happens, it's on you as the person who have done this. I have my Postgres runs with fsync equal off, and the other option, full page writes, are off. And the reason is because I want my test runs to run as fast as possible in Postgres, and I don't care if the database crashes, because if it crashes, my whole test is done. I create the database from scratch anyway. It's all test data, and I'm not testing really performance or anything. I want my test cases to run as fast as possible. So that's the goal. So I turn this option off in my Postgres instances for these test cases that I write on Postgres. And I see a significant difference. It makes sense, right? For that case. For other cases, production, absolutely, you have to have it on. Right? And you have to at least have it on and configure it such that on commit at least flush those changes to disk, right? I think the option to have it on open is slightly costly. And the reason is because every single write is doing an fsync technically, right? Whether that's a data fsync or a full fsync with the metadata of the file system. And that's something you have to kind of watch that, and you can configure that parameter in Postgres. Again, this is not a configuration or a tuning video per se, but boy, you can do so much in that case, right? This thing is just so interesting, but it tells you there's so many layers to this thing, right? So as a summary, the disk definitely lies, and the database definitely suffers as a result. That's why we expose all these configurations to the user, like to us. We need to know about this stuff. That's the truth. The truth is we are dealing with these many layers. So to hide all of this is such a lie, right, to the application developer. We should never hide anything, right? That's why I wrote a blog about that. Never make your API simple. If your thing that you're building is complex by nature, right? It's the way it is. Expose almost everything to the user, to the consumer. You can disagree with me, but by exposing everything, you show the consumer everything. And that's what databases do. The database never hide it. In fact, they add more and more configuration and options because you will never know how people will use your API, right? It's such a complex thing, and we're dealing with complex thing. You have two options. If it's in complex by nature, then expose this complexity to the user. Let the user feel it. Let the user have the option to pick and choose. You can't say, oh, just write, boom. No, what does that mean? Like there's all sorts of magic happening behind this API. You have to tell me what's going on, right? Otherwise, I call write and then, oh, but I called write. My data is not in disk. Why? I thought I called write. No, because you don't understand all these things behind that. Eh? Again, it's just interesting to go through all this and trying to make sense of all that stuff. The other option, as I said, is try to make the whole thing simpler, which is also an option. But that, my friend, you are alone, because nobody did that. Nobody have written, as far as I know, a system that talks directly to the disk drive. Directly. Because it's a very big task. You have no idea how much work the operating system is doing. If you want to skip the OS, or you want to skip part of the scheduling, the CPU, the instruction management, all this, the memory controller, the virtual memory system, it's a complex thing. If you want to discard all that and make your app simpler by saying, I don't need any of that. Just give me direct access to the physical memory, direct access to the CPU. I'm going to write my own instruction set for that CPU, right? And I'm going to write directly to this disk. You can kiss portability goodbye, of course. And that's what Apple, in a sense, is doing. They're just making their own proprietary stuff, such that all this CPU, the disk drive, the memory, everything is in one chip, right? But the disk is in another. Right? But then, if they have control over all of this stuff, then they can maximize the performance there, because they know every in and out there. There's no like open portability of this. That's another trade-off you're playing. But if you want to really jump to the absolute performance, you have to cut the middleman. That's not an easy job. At the end of the day, the disk lies. So watch out for the lies of the disk. How do you know? I'm going to reference, by the way, a blog. Hopefully I can find it, about exactly that problem, how flush actually is just being ignored, right? Even if the SSD doesn't have a battery powered system, sometimes just decide to ignore it and says, hey, I am going to buffer it for a few more milliseconds. And this is a decision that the SSD controller does. And can you crash in the middle of this and lose data? Sure. That's why you take other contingencies, right? That's why building a production system is complex, right? You have, you can't lose power, because even if you lose power, there is another system that immediately generates the power, so you don't lose it immediately. The server itself has a battery packed, right? Backup battery, such that even if you lose power, there is a backup place. So there's always a backup of the backup of the backup. And the whole thing is very interesting to me. All right, guys. See you in the next one.